Okay, I think we can start. Can you hear me?
Yeah.
So let me share my screen. Okay, you can see the screen, right? Okay, so this exercise section will discuss QED, and to understand QED, we first have to understand the equation of motion of relativistic electron, and the equation to describe electron is the Dirac equation written here, and since most of the time we're interested in free particles, so we can just substitute the plane wave solutions into the Dirac equations. And so I think in lectures we have derived ones, so I just show the result here. So the K can be plus or minus P over H bar, and for the positive one we have two independent solutions, and for the minus one we also have two independent solutions. And here the U1, U1, U2, V1, V2 are the so-called four spinors, and for the upper two we call them the positive energy solutions or the particle solutions, and for the lower two we call them negative energy solutions or antiparticle solutions. And here I want to talk more about these negative energy solutions because I think some of you may feel very confused about that. And why is this called negative energy solutions? Because if we consider the time phase factor, here E is greater than 0. So we can, when we write them back to the normal convention, it actually represents an energy of minus E. So that's why we call it a negative energy solution. And the problem is that we actually cannot observe a negative energy particle in our physical world. So the problem is, what does this negative energy solution describe physically? So to understand this, we can consider the equation of motion of electron in coupled to an electromagnetic field. And this is described by these equations. And you don't have to memorize this. It's just some additional stuff. So anyway, to describe an electron in electromagnetic field, we'll use these equations. And Q is the charge, and this is the 4 potential, which represent the electromagnetic field. And after some mathematical treatment, we can prove that this equation is actually equivalent to these equations. So in principle, we just take the complex conjugate and play around with this gamma matrix, and we can prove this. So you can see that these equations have the same form as the first equation, except that the charge is flipped. So we have two equivalent equations here. And now we turn off the electromagnetic field so that it becomes very, very weak. And now the equation 1 will just become the normal Dirac equation. And we know that this is a solution. And since it is a solution to equation 1, we can just substitute into equation 2. And you can try it yourself to prove that this is actually equals to this. And you can see that this is actually a positive energy solution because it has a normal time dependence, but it has a opposite charge because in equation 2 the charge is flipped. So that's why we say that negative energy solution will describe the antiparticles. And this is what we observe physically. So to make it more clear, in these equations, we have two positive energy solutions and two negative energy solutions. And in these equations, we also have two positive energy solutions and two negative energy solutions. But in physical world, we can only observe the positive energy solutions. And now from these relations, we know that these negative solutions actually correspond to these two positive solutions. So that's the idea. So anyway, the two negative energy solutions will describe the antiparticles in the physical world. So that's how we interpret the negative energy solutions. And I also want to talk about the Feynman-Stackelberg interpretations, which is also a way to understand the negative energy solutions. And the idea is that we take the negative energy solutions and do a time reversal transformation. That means we change t to minus t. And now it shouldn't be equal. So after the transformation, we can see that we obtain back the normal time dependence. And so people will say the negative energy solution traveling backward in time will correspond to the positive energy antiparticles. And that's why in Feynman diagrams, we'll use the arrow traveling backward in time to represent antiparticles. And under this interpretation, we can also understand why antiparticles have opposite charge. So initially, we have a negative energy electron, and we make it travel in a B field, and then we transform t to minus t. So we just play backward. So the negative electron will just reverse its path, and in this case, we'll actually see this particle have an opposite charge because it moves in an opposite way, and that's why we say antiparticles have a opposite charge. So so anyway, it's just an interpretation to the negative energy solutions, and it physically describes a positron with energy E and momentum P. So that's just a summary of what we learned so far. Okay, so let's go to the exercise questions. And the first question is to prove that the gamma matrices in the Dirac representation indeed satisfy the anti-commutation relations. And just a note, if we write this anti-commutation relation more rigorously, it should be like this. On the right-hand side, it should be a 4 times 4 matrix. So that means, for example, if we write gamma 0 back to this 4 times 4 matrix form, then it will be 2 gamma square. And we can use this 4 times 4 matrix and substitute into this. And it should be equal to 2G 0 0 1 1 1 1. So there's a hidden identity matrix here. But for shorthand notation, we just omit this identity matrix. And you can, in principle, you can just expand all this matrix into 4 times 4 matrix and substitute into this relation and prove that they are equal. But we usually just use the 2 times 2 block for simplicity. And I want to demonstrate it here. For example, for gamma 0, and we can use the 2 times 2 block. And it just equals to 2 1 1 0 0. So it just equal to 2G. And similarly, we can consider gamma I. And similarly, we can use this directly, use this 2 times 2 block. And it should be like this. And a property of the Pauli matrix is that the square is always identity matrix. So it's like this. And so this is equal to GII. And we can then consider when the index are not equal. So first consider 0 and I. And similarly, we can just use the 2 times 2 block and we can prove that is indeed 0. And lastly, we can consider gamma I, gamma j, where I is not equals to j. And you can expand. And in the last step, we can use another property of the Pauli matrix. So this is the anti-commutation relation satisfied by the Pauli matrices. And since we are considering I is not equal to j, so the final result will be 0. And so indeed, is 0. And so we have proved this anti-commutation relation. So it's just simple substitution. So let's move to the next question. So it's quite long. So let me first explain the question. So as I just said, in the equation, we have 4 solutions which carry the 4 spinors, U1, U2, and V2. And we know that U1 and U2 will describe electron, and V1, V2 will describe positron. But I haven't said any words about the spin. And it's a nice idea to interpret U1 as spin up electron, U2 as spin down electron, and V1 as spin up positron, and V2 as spin down positron. But actually, the 4 spinors does not have a definite spin, because when we consider the spin matrix and add on these 4 spinors, we can easily prove that in general, they are not eigenstates. So actually, we cannot interpret them like this. But under some special case, for example, if we choose the z-axis to point along direction of motion, we can prove that they will become eigenstate of the spin matrix. And we'll prove this in this problem. And the A part, we have to prove U1 can be simplified like this. So we just take the expression of the U1 spinor. And since we have put the z-axis along the direction of motion, so this just implies px/py equals 0, and all the momentum will go to pc. So we can just substitute this, and it will become like this. And next, we can use the energy momentum relations and replace the pc by this square root, and it can be simplified to this form. And lastly, we just use the expression for the normalization factor and substitute it. And finally, we can simplify to this form. And we have defined A plus to be this vector and A minus to be this vector. So that's part A. And in part B, we do the same thing. So we just use the expression for U2 and we just make pxpy to 0 and use the energy momentum relation. And lastly, we just substitute back the normalization factor. And the final answer is like this. And it's almost the same for V1 and V2. So I don't repeat once again here. So in summary, the 4 spinors will be like this. If we put the z-axis along the direction of motion. And in the last part, we have to find the eigenvalues of this eigenstates. So we can just add the spin matrix on these spinors. So for U1, can find that it is an eigenstate with eigenvalue h bar over 2. And for U2, it's minus h bar over 2. And for V1, it's minus h bar over 2. And for V2, is h bar over 2. So for the 2 positive solutions, we can just interpret them as spin up electron and spin down electron. But for the negative solutions, you may think that this will describe a spin down positron because it's minus h bar over 2, and this will describe a spin up positron. But actually, it's not the case because here what we find is the spin of the negative energy solutions, and it is not necessarily equal the physical spin of the positron. And to understand this, we can use the Dirac C picture to understand this. So in Dirac interpretation, all the negative levels are filled by these negative energy electrons, and he regards positron as missing negative energy electron. So so now let's excite a spin up electron in the negative C. So what we'll see will be like this. So there's a spin up electron here, and here there's a missing negative energy electron. So it will be regarded as a positron. And since this electron is spin up, and by angular momentum conservation, this positron should be spin down. So actually, it's missing negative energy spin up electron will correspond to a spin down positron. And that means the physical spin of the positron is opposite to that of the negative energy solution. So is it clear here? So the key is that the property of the negative energy solution is not necessarily equal to the physical property of the positron. So we cannot just say that when eigenvalue is h power over 2 and it means spin up positron. So it's not correct to make this conclusion. So we have to think it in more complicated way.
Can you explain again how come the angular momentum conservation leads to the positron having spin down?
So so this picture is something like we put some energy into vacuum and we just produce a electron positron pair. So that's so by angular momentum conservation, if the electron is spin up, then the positron should be spin down.
Okay, I get it. Thank you.
So, this is just a simplified way and a pictorial way to understand this. If you want more vigorous explanation, you can go back to this. So I've so here we say so we have this. So V1 will actually correspond to U1. So since U1 spin up, so V1 should also describe a spin up positron. So yeah, but anyway, the negative energy solution spin is opposite to that of the physical spin of the antiparticles. So in summary, we have spin up electron, spin down electron, and this will be spin up positron, and this will describe a spin down positron. And that's when we consider the z-axis pointing along the direction of motion. If we just arbitrarily choose our axis, then in general, it will not be an eigenstate of spin. So it will not have a definite spin for each spin. So for the last question, we know that under Lorentz boosting, the spinner doesn't transform like 4 factors, but instead they transform in this strange way, where S is a matrix like this. And we want to show that S dagger is not S dagger S is not equals to 1. And this result is used when we want to prove that psi dagger psi is not a Lorentz invariant. Because if we consider this and substitute psi prime to be S psi, then you be psi dagger S dagger S psi. So to prove that this is Lorentz invariant, we should have this equals to 1. and we will show that this actually not equals to 1, and so this is not in Lorentz invariant. So so first we just obtain the Hermitian conjugate. So we just do the complex conjugate and take the transpose. And here all the elements are real, so we just take the transpose. And it's also symmetric, so S dagger is just equal to S actually. So we just simply multiply them together. And you can see that, you can already see that it obviously not equals to 1. And the diagonal element will be like plus equals to gamma. And the off diagonal element will be minus 2. So this is not equal to 1, and this is not equal to 0. So it cannot be an identity matrix. So that's question 3. And yes, that's all about the exercise questions. And if you have any question, you can ask now, or if no, then you can leave. Okay, goodbye.
Can I just go back to the angular momentum thing of the spin up and the spin down of the positron? Because I was wondering, why can't we just say that the angular momentum or the spin of the positron just work differently? Like, yeah, why can't we just say, okay, the angular momentum of the positron just somewhat violated, or the spin of the positron just defined that way? Like,
yeah, you can define
because I mean the entire anti-particle thing is just made up, so why don't we just make up the angular momentum as well?
What do you mean by made up? Yeah, it's
we
not
literally,
physical, but it really corresponds to antiparticles which we can physically observe. Yeah,
right. That's why I'm thinking, why can't we just say, okay, I mean, even the concept of spin is kind of made up in some sense, because I mean, spin up and spin down, nothing is really spinning. So why don't we just say, okay, the positron, when it have that, so what I'm thinking is, why can't we just say the positron is spin up, but it's so let me think. I forgot what exactly the spin value you're.
Yeah, here we have a spin matrix. So,
right.
So we have defined this spin matrix. So when we act, so we can infer the spin from the eigenvalues.
Mm-hmm.
So that denotes the spin of the spinors. But the problem is that this is just the spin of the negative energy solutions, and it doesn't necessarily imply the physical spin of the antiparticles which we observe. So we have
Right, but
to
go on.
have this argument to argue that they're actually opposite.
Right, that's what I'm thinking. Why can't we just say, instead of saying that the physical spin is opposite to the solution itself, why don't we just say that the physical spin is whatever spin value you get from the solution, and it is the mechanism that the spin of the antiparticle works that kind of cancels it. So instead of saying that you need a spin down antiparticle for the angular momentum to conserve, why don't we just say that you need a spin up particle and a spin up antiparticle to cancel the angular momentum?
Mm-hmm.
I mean, because the up down thing is already made up in some sense. So I think in some sense it's still fine if we just say, okay, a spin up particle would cancel with a spin up antiparticle. And that's in that kind of manner.
Actually, I don't understand what
So
you mean, because
here is saying that.
So let me so when we put some energy into the vacuum, we'll produce a electron positron pair, and because spin is the angular momentum is 0 at initially. So after creating this pair, if we find the electron spin up, then the positron have to be spin down.
Right, but because here you imagine a spin up thing need a spin down thing to cancel each other, such that the angular momentum, right? But what I'm saying is, why don't we just say that for a particle, like a normal particle with spin up, you need a spin up antiparticle to cancel it instead of a spin down antiparticle to cancel it. So in other words, the spin in the antiparticle somehow works differently.
No, here we are talking the same spin, that the physical spin for both electrons and positrons.
But afterward, there's nothing spinning after all. So why don't we just say the spin of the antiparticle works somewhat differently?
Yeah, but we can measure the spin, right? They can be measured
you measure
in experiment.
The measurement of the spin is also some induction from the magnetic field, from the mostly the magnetic field of their measurements. But
yes,
I mean
that
you go on.
Yeah, you can just think this positron is a new particles, and we have two particles here, and we measure their spin, and they have to be opposite. It doesn't matter whether they are antiparticles or what. No matter when we produce two particles in vacuum, they have to be spin opposite.
No, what I'm thinking is why can't we just say that the antiparticles are something that works differently?
Why?
Because I mean the entire concept of antiparticles.
But if you don't know anything about the Wire equation, and in experiment you find two particles, and they have same mass and opposite charge, and have opposite spin, and that's all. You won't say we define differently for one of the particles.
Wait, no, hold on. But also, you in the mass, you wouldn't talk about negative mass of the antiparticle, right? You would also talk about just a positive mass for the antiparticle. You wouldn't say that because the antiparticle has negative energy, that's why we call it negative mass. You wouldn't do that, right?
Mass is always positive.
Right, then. No, but there is a question in chat.
What does the spin ion value negative energy? So you just imply the spin of that negative energy electron. And negative energy electron is not physical. So what we are interested is the physical spin of the positive energy positron. And the argument here is just to saying that they are opposite to each other.
Well, okay, how about this? How do you define what is physical spin?
Physical is just what we measure in experiment.
But you don't exactly measure the spin. Like you can't point at a number and say this is a spin. You're probably measuring something like the magnetic moment or the magnetic field or something like that. So there is nothing like a number that you can measure that represents the spin directly, right?
No, in experiment we can, well, given a particle, we can so I don't know. I actually don't know what's your confusion about the spin, because
no, I'm not confusing. I mean,
for every particles we can if they are in a definite spin state, then we can always assign a spin for them, no matter whether it is electron or positron or some or other thing. That's the physical spin.
I mean, as you also mentioned, the spin is something we assign to it.
For physical spin, we measure them, and in theory, we just add the spin matrix to the states, right? And the thing, and the key thing is here is the states here does not actually is not actually the physical state.
Maybe you address the question in the chat box first, I think.
Okay, yeah, that's very confusing. Yeah, antiparticles that we can measure in reality is always positive energy. And the negative energy solution here, they just correspond to the antiparticles, and they so do you know what I mean? So as I said here, we have two positive energy solutions and two negative energy solutions. And for these equations, we also have two positive and two negative. And what we can see in reality is these four. But mathematically, we will use these four solutions. And how we interpret these two negative solutions is that they actually correspond to these two positive solutions, which is really the antiparticles. And what we are doing just now is acting the spin matrix on these four solutions. So that's why when we act on the negative solutions, the eigenvalue doesn't reflect the true spin of the antiparticles. Because if you want to actually obtain the true spin, we should act on this solution. Is it clear?
But I mean, how does one solution more superior than other solutions? Like, why do you say the positive energy of the other solution is what we
because when we use the negative energy solution and substitute into this, they actually correspond to each other. But with a flipped charge.
Okay, then why don't we just say, I mean, why do we choose to keep the energy being positive instead of saying that it has negative energy but with the same charge?
Because it's mathematically more easy to handle these four solutions.
This
four solutions for the same equation.
Right. Here, if you see the equation, the four solutions in a box, I mean, there is a negative energy solution with the same charge as the positive energy solutions. Then why don't we just say the particle have particles that have negative energy with the same charge as the particle?
Because that's not we see in actual reality. We don't. It's meaningless to say a particle have negative energy, and that's why to interpret this we have to use the concept of antiparticles.
I mean, putting an I in an equation doesn't mean anything as well.
What? What are you saying?
You said negative energy is not meaningful, but I mean, sometimes putting an I in an equation doesn't make it more sensible. I gamma squared, I there.
You mean this I?
Yep.
Yeah, it's just mathematics. So you just do some, for example, take the complex conjugate and multiply some gamma matrix, and you will end up in this.
But the other thing is, why do we say negative energy is not meaningful? Because energy is a relative concept. There's a threshold that you refer to, and then you said this is called this is called zero energy. And whatever energy that you measure is with reference to this zero level. So why can't we have a negative energy? It's fine, right?
That's for potential energy. And here we are considering three particles. So it only has the mass energy and the kinetic energy. And for particles at rest, the kinetic energy is just zero, right? So the minimum kinetic energy is zero.
Yeah, but why can't we just say the antiparticle, when they move, they have negative energy?
We can't say that because so in reality you cannot so just assume them they are new particles, and when you just measure their kinetic energy and they should be positive. You cannot define you cannot just define a different rules for some particles, right?
But you literally made up this particle.
How do they actually exist? How do we make up them? They actually exist. But if you don't label them, we just label them as particle A, particle B, then we can just measure their kinetic energies. They are not.
There's another in the chat box as well.
Particle comes. How to understand antiparticles carrying positive energy when mathematically? So that's yes, so mathematically, we have two negative solutions, but we want to interpret, have a more physical interpretation, because in reality, when we measure the energies, they are positive. So we want to interpret them as a confusing. Yeah, do you understand this these relations? And these relations just imply then these two negative solutions actually is equivalent to these two positive solutions in these equations. And these two equations are equivalent. So we can say the two negative solutions correspond to these two positive solutions. And so that's why we interpret these two negative solutions as the antiparticles.
Actually, I've now another question. Like when you say the two equations are equivalent, what does it even mean by equivalent?
If mathematically equivalent, right?
Yeah, but mathematically equivalent is an
if you
equivalent
multiply say 2 here, then they are equivalent.
What do you mean?
Right? When you multiply 2 here, the solution so the equation is also whole, right?
I mean, but if you
put the complex conjugate for each thing, for each stuff, it also holds, right? You just another form of this equation.
Don't get this.
But because this, when you multiply 2 on both sides, they are the same.
Yeah, but you're just acting on the first equation there. You put a 2 on the first equation. How does that have anything to do with the second one?
But so okay, let me find that out. So first, for these equations, when we can take the complex conjugate, right? Do you agree on this step?
Mm-hmm.
So that, and then we multiply I gamma 2 on the left hand side.
Mm-hmm.
And let me see.
Okay, I believe you can do a number of operations to bring from equation one to.
That's basically the idea.
Okay, but now here's the thing. Now, if I have like a quadratic equation or simple equations, if I say two equations are equivalent, then I would expect the answers, the solution to that equations to be equivalent as well. Then why do we have two different sets of equations? I mean, two equivalent sets of solutions, like two.
Because here the variable become this. What is so you can regard this as a new psi. So when we solve, so in the first equation we are solving for psi, and for the second equation we will solve for this. And these two set of solutions are equivalent. The four independent we will have four independent solutions for equation 1 and also for equation 2. And that provides a way for us to interpret the negative energy solutions here. It's just an interpretation.
So you're saying, in order to understand antiparticles carrying positive energy, you need to have on the original solution side add an conjugate to it, a complex conjugate to it, and then you add a gamma 2 squared to it, and then add an I to it, and then all these things to make the energy. I mean, this is so made up, the entire thing.
Yeah, it's quite made up because in physical world, we don't observe negative energy solution. So we want to make up some argument for us to understand this.
Whoa, hold on. But
yeah, so
okay, let's say we forget about these things. Just think of some other physical scenario, and let's say there is an equation, and then we solve for the charge of an electron. Let's say, and then we solve it. Originally, we solve it as a negative solution. Okay, and because both sides, I mean, the equations is something, a bunch of symbols equals 0. Okay, then I can add a negative sign to the entire equations, and it is still. I mean, along these lines of proof, I can say that the new equation with a negative sign is the equivalent equation. And then the solution that I get would be a negative of my original solution. Then I could also say that the electron now have a positive charge. Why can't I say so?
If you add negative, then here you have an I in front, the minus sign before the I, and you also change the sign for the plus M. Then we cannot.
No. Let's say we're talking about other kind of equations. not necessarily this one. And we just call the minus psi is the new solution that results with the psi prime that you have here.
Yeah.
But now that the electron carries a positive charge now, because of the extra minus sign that I put there. But I mean the equations are still equivalent. I just put in the minus.
I think I've said these two equations have the same form except the charge, right? They are entirely the same except the charge, and the first term, the second term, they are all the same.
But you said they're equivalent because you just do a number of operations to bring from equation 1 to equation 2.
And now we define a new variable psi prime.
Right. I can also
and this
say
will be a solutions, and when we and this will correspond to another set equations, but with the charge flip. Only with the charge flip, and
never mind it. The other person he left with a question, but he has left.
observe perspective or not. Yes, is something like that.
Never mind it. I'll leave it here then.
But if you don't bother the physical meaning, then you can just regard these four solutions. Just blindly use these four solutions if you don't care what they mean physically.
No, the thing is not about they meaning physically or not, because the argument, I mean, if you think negative energy solutions are not physical, then I say the action that you put, like putting a I and a gamma squared and put an complex conjugate there, in order to make the antiparticles carries a positive energy, it doesn't. There's no good way to justify it.
Only in this way we can describe our physical world.
But
if you do it in another way, then I don't know what is that.
I mean,
and in this way, we know that they are antiparticles, and that's what we find in nature. All the thing we are doing here is just to explain the nature.
Right, but I mean, if negative energy is like somewhat not comfortable, then I say adding this thing in front in order to make it have a positive energy is equally uncomfortable.
Why?
You really had two things.
With negative energy is not uncomfortable because we don't find them in nature.
But why can't we just say that for antiparticle they carry negative energy? Just that
we don't measure them in our experiment.
But I mean, what if we say when we do measurement, we always only measure the absolute value of the energy? It doesn't break anything so far we have done.
If you think classically, that kinetic energy just means speed. Do you have negative speed?
But speed is a positive number. So why can't we just say that it?
So what does it mean for negative 2 minus meter per second?
No. What I'm saying is, what if we say that when we do measurement, we only measure the absolute value of whatever thing we are measuring? So for instance,
yes.
for a particle moving in an opposite direction, like, so for positive direction with a positive speed, it moves to the right, let's say. And then when it moving to the left, you say it has the same speed but opposite direction. But when you measure the speed,
Yeah, you are talking factor now. You are not talking about scalar.
Right. But, I mean,
if you don't consider direction, then speed is always positive. I don't know what is negative speed.
Yeah. Because you're measuring the absolute value of the speed. I mean, my argument, I mean, if you do all this thing to make the energy of the antiparticle from a negative energy to a positive energy, I could as well say that for whatever energy measurement we do, we always only measure the absolute value only. And that's why for all the time that we have measured, we only measure positive energy, positive speed, or positive whatever.
Yes, and in order to adapt to this convention, then we try to remove this negative energy and try to reinterpret this as positive energy.
I know. I mean, it's weird to say the least. Because in quantum mechanics, like non-relativistic quantum mechanics, the spectrum, the eigenvalue of that operator, the spectrum that you get is the observable. So in quantum mechanics, we just say that the observable, the value that you observe, is the spectrum of that operator.
Yes.
And now from the spin matrix or other energy operator that you get, the spectrum is that 2 of them are positive and 2 of them are negative. So why can't we just happily say that, okay, the spectrum is like this, that's why the measured value is also like this.
So here we have a bunch of negative energy states and a bunch of positive energy states. But here the energy is not potential energy plus kinetic energy. It's only kinetic energy plus mass energy. And kinetic energy in measurement is always positive. And that's why people just feel uncomfortable to this negative energy.
Well, then what is wrong with saying that whatever measurement we measured, it is always the absolute value of that energy? So what is wrong? I mean, what is wrong with this thing?
Well, if you just think Newtonianly, then they are half mv squared, always positive.
Right.
Related to the speed, can you explain what is -2 meters per second without talking about directions? You don't know what it means.
But with this thing, antiparticle and particle, I mean, whenever we enter the quantum world, there's an eye hanging around, and with an eye, you can happily say that I squared is a minus sign. So the speed of an antiparticle is just IV. So that's why when you take the square root of it, you get a minus sign. And this is exactly how you get rid of the minus sign in the first place. You literally put the I in front of the solution of the new side product there. That's why when you measure the energy, the I squared take a square and then you get rid of the minus sign.
Then why you treat electron and positron differently? Then you should use the same definition of energy for all particles.
Yeah, which is the spectrum.
Why for electron you say we use the normal V, but for positron we use IV?
No, I mean, if we want to have a unified definition for both positron and electron, we can happily say that whatever spectrum you get from the operator, for instance, energy operator in this case, whatever spectrum you get is the energy of that particle. So if the spectrum has positive energy and negative energy,
we are talking about measurement, not spectrum.
Well, but the spectrum is a measurement.
In measurements, you cannot measure positive, negative kinetic energy. So you are, I think you are saying we define so you haven't answered me to what does it mean for us to measure -2 meters per second for a speed.
It's just like the concept of spin. You just say the particle has a spin up and the particle has a spin down. Nothing is spinning, nothing is up, nothing is down. It just has a spin up and a spin down. And so it can happily have a -2 speed.
Well, we are not talking about spin, we're talking about energy, right?
Yeah, what's the problem?
So we don't know what is negative energy.
Well, we don't know what is spin as well.
We know what is spin because spin is something like directions. So we have spin up and spin down. And for speed, we only have zero speed, 1 meter per second, 2 meters per second. We don't have -2 meters per second. So I don't know what's wrong with it.
But speed is just a number, right?
The number is associated with directions.
What do you mean the numbers associated with direction?
h/2 is spin up. It's related to a direction. It's not only a number. But for speed is
no, hold on. You can wait. The direction of the spin is determined by the direction of the spin factor. The eigenvalue just gives its magnitude. And if it's carrying minus sign, it just flip the factor.
Yes.
But that eigenvalue is the spin. Sorry, the spin value, the magnitude of the spin.
Yes.
Is positive or negative.
Yes. So what's wrong?
But it's just a value. It's just a magnitude of the spin is up or down. I mean, sorry, positive or negative.
Because we define the spin matrix like this, so that spin up will have positive h/2 and spin down we have -h/2.
But okay, but we can also have concepts like negative temperature.
Negative temperature.
In statistical mechanics, when you suddenly like drop the potential or turn it off or flip it the other way around, there would be a short period when the matter is under a negative temperature state. And we're happy with that.
Well, if you choose the absolute zero as zero temperature, then it's meaningless to say negative temperature. Yeah,
but there is a notion of negative temperature. There is a state.
That's not physical.
Well, no, it is physical. As I remember, what is happening is there is a bunch of electrons or something that has spin in a magnetic field, and you suddenly switch the direction of the magnetic field, and all of a sudden, all the states, they would because the spins are anti-aligned with the magnetic field. Therefore, that bunch of electrons will instantaneously have, momentarily, not instantaneously, momentarily have a short period of time when they carry a negative temperature.
How do you define temperature in this case? Is it the average kinetic energy?
Let me think. I'm not totally.
It depends on how you define temperature again. If you regard temperature as average kinetic energy, then it's again meaningless to say negative temperature.
But the point is, if we can like redefine things, so okay, but I think the statistical way to define temperature has to do with the partial derivative or something like that. I think it is the partial derivative of the partition function with respect to the, I forgot what, but anyway, but the thing is, if we can define, I mean, temperature is just a number, and we say that we are happy with those electrons having negative temperature because of our definitions. They have negative temperature. And why can't we just say that antiparticle has negative energy as well? I mean, as you also mentioned, all of these depends on definitions only. Then why don't we just say
just because in experiment we don't record negative, we don't see negative kinetic energy.
The energy that you say energy, you don't measure energy directly. You don't point at the screen or point at something and say that this is minus positive 10 joules or positive whatever joules. You just infer it from this velocity, charge, whatever, and then you calculate its energy, right? The same as the negative temperature, they don't actually point at something. They don't actually put a thermometer or something at the particles and then say that, okay, I measure negative temperature. The notion of temperature in this case, you can no longer put a thermometer in it and say that, okay, I measure negative temperature, something like that. It doesn't break the thermometer or something. They infer the concept of temperature from something else.
So let's consider particle at rest, mc square. So if you're talking about negative energy, then you are just saying you have negative mass.
Mm-hmm.
So what does negative mass mean? So for zero mass, it's just nothing.
Mm-hmm.
And then what is negative mass?
The antiparticle with mass m.
Then why we know that this is the antiparticle? Why we treat some kind of particles differently from other particles?
Because the solution.
So now I give you two particles, A, B.
Mm-hmm.
So and I ask you to tell what's their mass. What will you do? You just measure using a weight, and you will just tell me some number, 5 kilograms, 4 kilograms.
You can't measure them with a weight.
No, I mean,
at this point, the concept of mass.
So let tell me what is negative mass.
It's just an antiparticle with mass.
So how do you know a particle is antiparticle? I just give you two things here. Do you know which one is antiparticles?
Well, but if I put the matter particle and it's matter,
yeah, I just put it in a black box. You just don't know what it is, and I now tell you. You have to tell me what is their mass.
No, but I can know one of them are antiparticle if I smash them together. Because if I smash them together,
don't smash. Just give you one particle. You tell me your mass.
Well, no, you can't.
Then you will tell me a positive number, right?
A normal particle, you can't tell its mass until it decays.
How do you differentiate normal particles? All the things we can see is normal.
Well, I mean, what I mean is, even, I mean, whatever it is, particle or antiparticle, whatever, you don't actually measure its mass. You kind of measure its mass by doing something else with it. Let's say decay. You wait for it to decay, and then you measure the trajectory of the particles that is coming out, and then you infer the mass of the particle that was decayed from.
Yes. So
there is no
in this case you is same. You can only tell me a positive number.
Then what is so wrong of saying that? Come on. Oh, hold on. How about the charge?
Charge is not the same as mass. So you don't have so you cannot explain what is negative mass, right? You just focus on mass.
But I can choose. Same as what I can choose for the charge. I mean, in our current convention, we can't explain.
Mass is defined as the amount of matter, right?
But your
amount can only be zero. You cannot have -1 amount.
I mean, charge is the same. You can't have -1 charge in some sense.
But charge, we only charge is a quantity that we attach to a particle, which have
must be the same. I mean, mass and charge.
Mass is also a quantity that we assign to a thing, and it means the amount of matter, right? And amount it can only be positive. You can have one apple, 2 apples. You cannot have -1 apple.
Whoa, hold on.
Just so simple.
Hold on. But the charge is the same. I mean, the charge.
It's not the same. Why is the same?
Hold on. Let me finish first.
Charge is a quantity that we define for
Oh no, hold on. Because the mass and the charge, in some sense, is
You
also
only have one kind of mass, but they have two kind of charges. That's not the same.
Why can't we have two kinds of mass? I don't understand.
Why?
You can measure.
I give you a
electron.
bunch of particles. I ask you to measure the mass. Then you can only give me a bunch of positive numbers.
But the charge is the same.
So a simple question: what does -1 apple mean?
Well, how about you tell me what is minus charge means?
Well, we just have two particles that they travel in different trajectories in magnetic field. So we just assign one of them plus charge, one of them minus charge.
Well, then I can as well say that things that have minus mass annihilate with whatever thing that have positive mass.
So how about I just give you one particle?
No,
you determine the mass?
Just one.
For charge, we can determine the charge by only considering this particle in the magnetic field. But for mass, you can. Then you are saying we can only determine the mass when we have two of them.
But the charge, you have to let it interact with the magnetic field in order to determine its charge, right? For the mass, I can also do something with it.
So let's say this no, the problem is that mass is the amount of matter, and you don't have minus amount.
You don't have minus a charge as well. I mean, the mass and the charge is also like
charge is not something.
To the field,
charge is
right?
not amount. Charge is a. Do you know what I mean?
The coupling, like how strongly do you couple to the electric field is a charge. Like it tells you the amount of coupling, like how strongly are you affected by the electric field is what the charge tells you.
Yes, and we have two kinds of coupling.
The sign tells you what direction do you go.
Our discussion is more and more confusing now.
Yeah.
But
yeah, I mean, do you have anything else to do? I mean, if that's the case, I will let you go, I think.
What?
I mean, do you have any other business to deal with or something else to do?
Oh, no, but I haven't had my lunch.
Yeah, I think we can stop here. I mean, but thank you very much.
Yeah, well, yeah,
No, I mean, I'm not like, okay, the argument of like putting, like forcing it into a positive energy and those arguments, those things works fine, I think. But I'm just saying, like, why can't we just like define it the other way around? Like everything is just after definitions, like energy, charge, mass, whatever thing is just something we get after our definitions, and then yeah. Like, I mean, even the charge itself is also after definitions. Like some stupid guy found a couple hundred years ago said that electrons carries negative charge. That's why we live with it. And yeah. I mean, technically, if we are happy, we can also define not charge, but we define it like two things. I mean, a particle, instead of carrying a positive charge and negative charge, we can as well say that there are two properties of the particle. One is the amount of charge, like the coupling to the electric field. The other one is the direction of the coupling, and we can happily put two properties out of and that way the charge will always be a positive number. And so
let me think. So let think in this way. So a positive charge will attract a negative charge, right? But if we put two masses together, they always attract. That's why we only have one kind of mass. We don't assign something called negative mass.
Well, but for the charge, I mean, the mass. Wait, do we actually know that the antiparticles would attract to the matter particle?
What does it mean?
Like if you put two antiparticles together, do they actually attract to each other?
How you know a particle? So the problem is once again how you know this is antiparticle. If I don't tell you what is this. In reality, you just see something that just differ by their charge. And you just treat them equally. You won't say, oh, I assign a different mass for them.
Oh, hold on. Now I'm thinking about this because when you said the trajectory is up in opposite direction, I mean, in order to arrive at that trajectory, you need to use the F equals ma equations in some sense. I mean, in some ways, you need to somehow employ the equations.
Well, we just see by eyes. They are.
I know. What I mean is, okay. So here's the thing. The equation for the trajectory is something like the it is the Lorentz force equals ma. In order to arrive at that trajectory, you will equate the Lorentz force to ma. Now, we put that minus sign to the charge in the Lorentz force to take account for this opposite direction. What if we put the negative sign on the mass? I mean, it's the same equation. It's just the different position of putting the minus sign. In that way, I will still have you see the same trajectory is moving in the opposite direction.
So then you are just flipping the role of mass and charge.
But not really. Right. I'm just saying that I put the minus sign instead of to the charge. I put it to the mass. I'm not flipping the
So what's the meaning of flipping this minus sign?
Then that way you will have an antiparticle carry the same charge, same positive charge, but moving in different direction. But now your explanation would be because they carry negative mass. That's why they move in different way.
Now then in this interpretation, then all the particles in universe will have only one kind of charge, right? And yeah, and that's what the Dirac equation give us. So all the solutions are negative charge, and we have plus positive mass and minus mass. That's what the solution give us. And people just don't like negative mass, because mass usually refers to amount of matter, and we don't know what is negative matter. So we just yeah, I think you are partially right that we can actually redefine all the things, but that's just
yeah, that would be a big mess.
Yeah, I think that's the case. So that will violate our first impression to what mass mean.
Yeah, probably does. Maybe
Yes.
I probably have to read more about this, I think.
Yeah.
But thank you so much.
Okay, thank you. I think I have to have lunch now.
Yeah. Oh.
Yeah. Very good questions.
Yeah. Thank you so much. I'll see you next week then.
See you next week.
See you. Bye-bye.
Bye-bye.